Hello everyone, I am Dr. Jagadha, Associate Professor in the Department of Mathematics. Today we are going to discuss about Cayley-Hamilton theorem. Throughout this lecture, we are going to focus on definition of eigenvalue and eigenvector, find the eigenvalue of your matrix, find the inverse of your matrix, find the higher powers of the matrix. What is definition of eigenvalue and eigenvector? Let capital A equal to Aij. That is, this capital A, it's nothing but the matrix, the name of the given matrix, it's denoted by capital A. Aij, this I stands for rows, the J stands for column. That is A11, A12. The position of the elements in the matrix, it is denoted by Aij, where I denotes rows, J denotes column. Be an n by n matrix. N by n matrix, that is, we understood that is a square matrix. That is, n by n, it's order of the matrix. Now if you're saying the both are same, that is, it indicates that the given matrix, the number of rows and number of columns, both are equal. Both are equal. That is what this is, square matrix. A non-zero vector capital X. A non-zero vector capital X. What is that meaning of it? Non-zero. That means it is not zero. This capital X should be a non-zero vector. So this is zero vector. This capital X should not be a zero vector. Now, non-zero vector. So this, the X should be like this, non-zero vector. Is said to be a characteristic vector of capital A if there exists a scalar lambda such that Ax equal to lambda x. Now this Ax equal to lambda x, this A is nothing but given matrix. This X is eigenvector or characteristic vector. Lambda is eigenvalue. If Ax equal to lambda x, where compulsory this x should not be equal to 0, that's what we discussed earlier. Capital X is the eigenvector or characteristic vector of capital A, that is a given matrix A, corresponding to the eigenvalue. Eigenvalue is, this is the lambda of capital A, that is the given matrix. So we have to be very careful. That is, the definition of eigenvalue is Ax equal to lambda x, where lambda denotes eigenvalue, capital X denotes eigenvector, A is our given matrix. Definition of Cayley-Hamilton theorem. Every square matrix, see the words, every square matrix. That means in the matrix, number of rows and number of columns, both are equal. Such a matrix, we will call it as square matrix. Satisfies, we will see with one example, exactly satisfies what is the meaning of this particular sentence. Its own characteristic equation. So this is the definition of Cayley-Hamilton theorem. We will see it. Before that, A minus lambda I, this denotes characteristic matrix. The same a minus lambda I, if we are finding determinant, then it is a characteristic polynomial in lambda. If the determinant is equal to 0, then it is characteristic equation in lambda. So we have to be careful remembering, and we have to record these notations in our memory space. So the characteristic equation of capital A is determinant A minus lambda I equal to 0. So f of x equal to x plus 2. It is one algebraic expression. It is given. Now this expression x place, I am going to substitute some number. Which number if I take x, I should get it f of x equal to 0. That means x place, I am going to substitute some number. Otherwise, simple thing, x plus 2 equal to 0, x equal to minus 2. So if you substitute here, so minus 2 plus 2, we are getting 0. Yes, this minus 2, it satisfies this expression. Algebraic expression, that's what we studied in the lower classes. The similar, that is the reason in the definition here also satisfies its own characteristic equation. That is the reason here determinant A minus lambda I equal to 0. I hope so. Now everybody understood. So it is written minus 2 plus 2. We are going to solve a problem using this Cayley-Hamilton theorem. We are going to verify it. So the given problem is capital A equal to, it's a 3 by 3 matrix. That is, it has 3 rows and 3 columns. 3 rows and 3 columns. So verify Cayley-Hamilton theorem and find A inverse and A power 4. The characteristic equation of capital A is determinant A minus lambda I equal to 0. So A minus lambda I first initially we will find. So the A place we substituted the given matrix, that is the given question. What is the matrix? It is given in the question. That the capital A we have taken, we substituted in that place. The minus, it is written as it is. This lambda also, it is written as it is. I, that we have taken the unit matrix, but specifically we have taken 3 by 3 unit matrix. The reason why we have to take 3 by 3 matrix, here the order is also 3 by 3. Specifically why it should be taken 3 by 3, why it is not 2 by 2. The reason is, we know it, here this operation is subtraction. Whether the operation is subtraction or addition, compulsory both the matrices should be in same order. That is the reason here it is taken 3 by 3 matrix. Here this step, it is copied as it is. Here lambda it has taken. Here, minus it has taken as it is. The lambda we have taken inside. Lambda into 1. That is the principal diagonal. The changes occurred. Because here the principal diagonal, the element is 1. So lambda into 1, the same lambda, lambda, lambda. The remaining and all 0 elements. Because 0 is multiplied with anything, we will be getting the value 0. So this is the matrix. Finally, we got it. Okay. Next, we are doing the subtraction. Subtraction also, we know it here. The changes will be only in the principal diagonal only. So we can see it here. Because remaining and all the values will remain the same. The reason is 1 minus 0. This one. Same only 1 will come. Because 0 is playing the additive identity. It won't change the value. Next, 2 minus 0, we will be getting 2. So then where the changes are going to come? In the principal diagonal. That is 2 minus lambda. Yes. 3 minus lambda. Fine. Minus 2 minus lambda. So the changes occurred in the principal diagonal. Remaining elements, they are written as it is. Now, what is the characteristic equation? That is determinant a minus lambda I equal to 0. So the determinant, it is written this matrix. We have found the determinant here. The symbol is this, both the parallel lines. Yeah, this is the matrix. We got it. The determinant, we have to do it. Okay. This determinant, 6 ways are there. So this is what R1. This row is R2, R3. Either these 3 way we can expand. Otherwise, C1, C2, C3. This way we can expand. Any among these ways, any one way we can adopt. Here we are adopting here R1. According to this R1, I am expanding the determinant. I'll tell very slowly. Please concentrate it. So now R1. So this position I am taking. When I am taking this position, where that element position, particular row and particular column should be neglected. The balance one, we have to find the determinant. That is the cross multiplication, we have to do it. So this is the cross multiplication. This into this minus of this cross. So you can see it here. 2 minus lambda. This into this. That is 3 minus lambda into minus 2 minus lambda. Minus of this cross. It's fine. So the R1, the first element we completed. The second element we are moving. The second element, the position it has negative sign. That is the reason here negative sign is there. Next, this position I have taken. That means this one. We can see in the rough column. This position. So that means this particular column, this particular row we have to neglect it. Balance we have to do the cross multiplication. Here itself if I do, the confusion will be there. That is what here separately it is written for the understanding purpose. So now this particular column, particular row, it is we are neglecting. The balance one, the remaining one, we are going to do the cross multiplication. That is 5 into this one. Yes, fine. We got it. Minus of this cross. Minus of this cross means minus 3. Minus of minus 3 plus 3. Fine. Now R1, this is we completed. This also we completed. The balance one R1 is the last, the third element. This position is positive. That's what it is written, plus 2. So if we are taking this one, this particular row, this particular column is neglected. The balance is only, this is our balance. This balance we have to do the cross multiplication. That is this cross, 0. Minus of this cross. Always the cross multiplication determinant, the upper cross minus of this lower one. So 5 into 0, 0 minus of this cross. That is minus 1 into 3 minus lambda. So minus into minus plus. So we got it. So 2 minus lambda. Next 3 minus lambda. This as it is. Next minus 5. This as it is plus 3. Next. So just actually simplification only it is written. Just these zeros are removed. Next. 2 minus lambda as it is. Here the simplification. 3 we are taking inside. 3 into minus 2 minus 6. 3 into minus lambda minus 3 lambda. Minus lambda into minus 2 plus 2 lambda. Minus lambda plus lambda square. Next, the minus as it is. 5 into minus 2 minus 10. 5 into minus lambda minus 5 lambda plus 3. 5. Next, 2 into 3, 6. 2 into minus lambda minus 2 lambda. Now, just it is written, the previous one. Yeah, we can see it here. 2 minus lambda minus 6 minus 3 lambda plus 2 lambda minus lambda plus lambda square. So, minus this 2 minus 7 minus 5 lambda. So, this as it is written 6 minus 2 lambda. Next, we are taking this 2 inside. That is 2 into minus 6 minus 12. 2 into minus lambda minus 2 lambda. 2 into lambda square, 2 lambda square. Minus lambda minus 6 is what? 6 lambda. Then minus lambda into minus lambda plus lambda square. Minus lambda into plus lambda square is nothing but minus lambda cube. Then minus we are taking minus into minus 7, it's plus 7, minus into minus 5 lambda plus 5 lambda, 6 as it is, this minus 2 lambda as it is. So now, this just your simplifications, where any cancelling is there, we can say this is written as it is. 3 lambda square, here 1 lambda square is there, yes. Here 2 lambda square, it is becoming 3 lambda square. Then here minus 2 lambda, here 6 lambda, here 5 lambda, here minus 2 lambda. That is 11 plus 11 minus 4. So plus 7. Next, here minus 12 is there. Next we can see it. Here plus 13 is there. So that is the reason here plus 1 equal to 0. Just what is that? Here keeping as it is also it's okay. But normally we will keep lambda cube as a positive. If you are keeping negative also, nothing wrong in it. So just we wrote the opposite signs. So lambda cube minus 3 lambda square minus 7 lambda minus 1 equal to 0. So we got a cubic polynomial in terms of lambda after the solving that is the characteristic equation determinant a minus lambda I equal to 0. So now to verify the Cayley-Hamilton theorem, we have to show that is what is a cubic polynomial. We got it in terms of lambda because every square matrix satisfies its own characteristic equation. That is the definition of Cayley-Hamilton theorem. According to that, what we got the polynomial lambda cube. In terms of lambda, we got it. So wherever lambda, we are replacing the lambda by capital A. So we got it now. A cube minus 3a square minus 7a minus 1 equal to 0. Yeah. Now, just this is one matrix. Here minus sign is there. This is one real number. Is it possible to subtract it? It is not possible. Why here the point is coming here? Because here a cube is a matrix, a square is a matrix and 7a is also in the form of matrix. Whereas this 1, it is a number, real number. It is not any matrix. It is not possible. We know it. The starting only, initially only we discussed that addition or subtraction of matrices. Matrix is singular, matrices is plural. So the matrices addition or subtraction, the order should be same. But it's a real number. It is not possible. That is the reason here one small example it has taken here. This is a 2 by 2 matrix, subtraction one real number. It is not possible. So now, how to make it possible? 9 into, it should be some multiplied by some I, unit matrix. Then it is possible. This I, we will take it as what? Some 2 by 2 matrix. Then we can do the subtraction. Based on this concept, here this 1 also it is multiplied by I. So 1 into I, we are getting I. So the next, so we can see it here. So this one, it is 1 into I, it is written I. That is the reason. Now A matrix it is there. First, to substitute in the equations, we know the value, we must know the value of A square. A, we know it, we will find out A into A. Yeah. How to do the multiplication? The first matrix, we will take the first row. Second matrix, first column we will take. Always the first matrix regarding row concentration. Second matrix regarding column concentration for matrix multiplication. That every student should remember. Now that is the reason here animation also. The red rectangular, that is a row. The green, that rectangle is column representing. How to do this multiplication? Now, this 2 into this first element, 2 into 2, yes, 4. 1 into 5, plus 5. 2 into this minus 1, minus 2. So, first row we have taken, we finished the work regarding first column. First row taking, complete all the columns of second matrix, we have to do it. That is 2 into this 1. 1 into 3. Yes. 2 into 0. Completed. Next, 2 into 2. 4. 1 into 3. 3. 2 into minus 2. Minus 4. Next, so first row we have taken, we completed the entire columns. Next, second row we will take. That is 5 into, second row taking, now first column, 5 into 2. Next, 3 into 5, 15. 3 into minus 1, minus 3. So second row we are concentrated with the first column, we got it. Next, second row with second column. That is 5 into 1, 5. 3 into 3, 9. 3 into 0, 0. 5 into 2, 10. Next, so here actually 3 into 3, 9 should come. This minus not there. 3 into 3, 9. 3 into minus 2, minus 6. So we completed the second row with all the columns. The leftover is third row, it is there. So minus 1 into 2, minus 2. 0 into 5, 5. Minus 2 into minus 1, plus 2. Minus 1 into 1, minus 1. 0 into 3. Minus 2 into 0. Clear. Next, minus 1 into 2. 0 into 3. Minus 2 into minus 4. Plus 4. So, we have to keep it in our mind. The first matrix related to row. First row work with all the columns of the second matrix. Next, second row working with columns of second matrix. Third row work with columns of second matrix. Very simple thing. So we got it. The simplifications. 4 plus 5, 9. This 7. 5. 4 plus 7 minus 4. Similarly, the second row we got it. 22, 14, 13. Third row we got it. 0, minus 1, 2. A square we completed. Now we have to do A cube. A cube, it's nothing but just now we got it A square. So A square into A. A square into A. A is our given matrix. Same way, before what we have done it, similar way multiplication we have to do it. That is here the first row, the first column. So 7 into 2, 14, 5 into 5, 25, 3 into -1. We complete first row taking first column we completed. Next second column. So one row taking, finishing the column, entire columns of the second matrix. So 7 into 1, 7. 5 into 3, 15. 3 into 0, 0. 7 into 2, 14. 5 into 3, 15. 3 into -2, -6. Fine, it's very simple. Now, second row, work with all the columns of the second matrix. So that's what we are getting this. Next, similarly, third row with all the columns. We have to do it. So simplifying, we are getting 36, 22, 23. 101, 64, 60. Third row, -7, -3, -7, we got it. So A cube minus 3A square minus 7A minus I equal to 0. So we are substituting, that is A cube place, we substituted the matrix, -3 is written as it is, then A square it is written as it is, then -7 it is written as it is, A matrix is written here, then minus I. Here 36 minus 21 minus 14 minus 1. Next 22 minus 15 minus 7 minus 0, this place. Next, the third position, 23. Here, yeah, this is 3, but here outside is -3 is there. -3 into 3, -9. Next, -7 into 2, -14, minus into 0. Second one, 101. Here -3 into this 22, -26, -7 into 5. Sorry, this is the second position. So 64, 3 into 14, 42, -7 into 3, 21. Here this is there. Next, the last position, 60, -3 into 13, 39, -7 into 3, -21. This is 0. The last, the row, just as it is, -7. Here, 0. Next here, -7 into -1, +7, this one. Next, my second elements, -3, -3, -1, +3. Next, -7, this 7 into 0, 0. Here also, the last one into this one, 0. Same positions. This matrix now, this position I am taking, every matrix, the same position, the values to be taken. So -7, here the position is 2, but outside -3 is there. -3 into 2, -6, -7 into -2, 14. Here -1. So it is written, we got it now, 0, 0, 0. 0, 0, 0 matrix, we got it. So every square matrix, that is our given problem. The matrix 3 by 3 matrix satisfies its own characteristic equation. That is determinant A minus lambda I equal to, we got it, the 0 matrix. We can see what we have done it this entire lecture. That is the given matrix A is given. Then we are the characteristic equation of, that is the definition of Cayley-Hamilton theorem. Every square matrix satisfies its characteristic equation. So that is the reason we found first A minus lambda I we found, that determinant we found which is equal to 0. When we are finding determinant equal to 0, we got one cubic polynomial in terms of lambda. Then the lambda is replaced by capital A. Then a cube minus 3a square minus 7a minus I equal to 0. This is also one place it is written I. The reason is every square matrix, the matrix, the addition and subtraction, the definition is where this addition and subtraction it is possible, the matrices should be in the same order. That is the reason the real number 1 is multiplied by that identity matrix I. So 1 into I we are getting. Here, to substitute here, we know only I matrix, we know it, we can write it. A is nothing but our given problem. A square we don't know, that is the reason A into A we found. To find A cube, with the help of A square into A cube we did. So these are the steps we followed. Then we got it, satisfying the 0 matrix. So we verified Cayley-Hamilton theorem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.